All right. Good afternoon, everybody. Happy Monday. You've got your PSAT this week. So in class this week, we're going to keep it fairly simple, very direct. Luckily, our unit kind of works out that we have surface area to deal with for this week, which is honestly, of like all the things, it's one of the easiest sections to get to because it's just more of area, right? It's not anything new conceptually. It's literally adding up multiple areas together. And the text has provided some shortcut formulas, some with the round shapes, the spheres and the cylinders, right? You had the little finagling there. But otherwise, not too bad, right? As far as completely new and different. So it's going to be kind of chill this week. That's why I got the relaxing music going. You can relax. I'll do one or two example problems along with you guys, just to point out a few of the major change-ups when you go from 2D to 3D, other things to keep in mind to help you go through the problems, then I'll leave you guys to get to work on those, all right? So here is what we will be looking at today. Surface area of, I would say, falls into one of two categories of shapes. You've got your polyhedra, okay? That is everything with hard corners, sharp edges, right? Made of polygons. Very simple surface area. Just add the areas of each polygon, okay? Nothing to it. There's some shortcuts introduced in the text. They can maybe save you a little bit, like, oh, well, with the whole, like, the perimeter of the base times the height. And you could do that. That's great. If you remember to use those shortcuts and they work for you, awesome. If not, just track all the shapes. And so the real trick then is keeping yourself organized. Okay? Make sure you work out, okay, how many of each? I've got 1, 2, 3 rectangles, 2 triangles. Okay? The triangles are identical. 2 of the rectangles are identical. 5, 5, 6. This bottom rectangle is not the same as the others. Do not multiply your rectangle area times 3. Okay? So you got to keep track of what is where. Do I have all the pieces? Which pieces are the same as which other pieces? That's the main issue with polyhedron. And then the other category of shapes is anything involving a circle. Right? So you get cones, cylinders, spheres, hemispheres. We'll throw that one in there. It's literally just half a sphere. Right? And dealing with those. And those ones you do kind of need to rely on the specific formula. Right? Because there is not this shape that is the cone itself, the part that wraps around. That doesn't come from another polygon. That's a new thing for this. Right? Other than that, it's just piecing these things together. Every problem here is working out how much of what shapes do I actually have to deal with. Okay? And then you get into these kinds of applications where the surface area is a big deal. Greenhouses. Right? The amount of heat coming in and out of a greenhouse is directly related to its surface area. So if you want to keep your plants warm in the winter, you need to know, or you ought to work out, how much surface area of a greenhouse you're looking for. I really like these two problems in conjunction here, because they give you two different designs of greenhouses, and they're about the same size. They're pretty close. 96 and 100, or 23 and 24. So this one's just a little bit bigger. Okay. But what does that mean about the surface area? How much more surface area is it going to have? Or does it have less surface area compared to the rectangular squares and triangles construction versus this dome cylindrical construction? Okay. I'll give you a hint. There is a reason you see more of these at the industrial place. If anybody has gone out to like a nursery to pick up little plants, okay, they've usually got a lot of these kinds of buildings out, don't they? There's a reason why. Figure out, do they want the most surface area or the least surface area? Which is it? There's a big difference. And we've got other combinations of interesting shapes. So I'm going to walk through one example here to highlight some of the things you'll need to deal with now that we're in 3 dimensions here with area. So first off, the surface area, again, is just adding up each piece. So you've got to keep track of the pieces. Okay? Notice this one. This is a very common feature with these 3-dimensional shapes. The SAT will love to throw these kinds of questions on you. They'll hollow something out. Okay? So it's not just a hemisphere. It's a hollow hemisphere. And we've got to work both sides. Imagine, if you will, this is a real thing. You got one hemisphere, and then you cut out the... So it's got thickness to it. It's a bowl, right? I want to understand that conceptually. Looking at this picture, might be a little overly dramatically thick, okay? But it's a real object now. It has thickness. It's got an exterior and an interior, both surfaces. Right? So if you were to paint this like I have painted my Batman bowl here, you've got to paint the outside, you've got to paint the inside. Right? It's perfectly round here, so there's no separate bottom like I've got here, but it does have a top edge to it. If you look at my bowl, I've kind of left that white. Okay, a little bit of splash over, but that itself is another surface. And so I want you to watch out for this hollowed out bit. This is kind of a key word here. That means you are going to need to add or subtract something. That just, when you see something is hollowed out, or you look at a picture, especially when you see the dashed lines there, they've cut something away. Okay? You might have to subtract something. Certainly if this was volume, we'd be removing all of that volume. In this case, we're adding a new surface. Now we've got to cover the inside. If this was a physical thing and you were spray painting from all angles, where's the paint going to go? Going to go here, going to go there, going to land inside, right? Everywhere the paint can land. That's the surface area you need to count. Does that make sense? Okay. So, with that in mind, if we were to find the surface area of this hemisphere, what pieces will we need? Just describe them. Don't be specific. What's one part that we're going to have to add up here? The height? The height is one surface. Give me like a side, right? We've got one semicircle, which is located where? One on the inside. Good. So we've got the inside hemisphere. And what else? What's another piece that we're going to have to add up here? If we got the inside hemisphere, we also have to include the outside hemisphere, right? And there's one more component to this. There's one thing we're missing. If we only colored in just this outer shell here and just this inside face here, what would we be missing? The what? Do you see it? What part have we skipped? You want me to actually color the whole thing? Okay, I'll color the whole thing. Go all the way to the inside and all the outside. What part is still not colored yet? The what? In between. How would you what would you describe that as? it's the difference size-wise, right? You've got the large outside and the smaller inside, so you need that gap in there, that gap that goes all the way around the top of the bowl, right? I'll just call it the top side. Don't overcomplicate it. But that is a ring, right? I looked at this from above, right, top-down view. Wouldn't I get one big circle and one slightly smaller circle inside? And again, it's a 3D physical object. It has thickness. So we have to include that edge. Okay, again, literally this top edge of my bowl, the part that if I was to paint all that, we could, use it as a stamp now. Okay? Does that cover all of the exposed surfaces? Yeah. Okay, so that's main thing number one. Make sure you get all the exposed surfaces of your object. Watch out for hollow portions, things being cut away, because you're going to have to subtract something. In this case, turns out that top ring is not just one circle equation. I'm going to have to take a circle minus a circle, right? We've done that before. We did area of a circle, subtract out a circle. So each piece by itself is not too bad. We just got to make sure we keep track of them all and add them together. So let's start with that. Let's find, we'll go different colors here. So we'll go inside first. That is a hemisphere, which is just a fancy word for half of. So we don't need a fancy formula for a hemisphere. We'll just take 1/2 times the formula for a sphere. What's the surface area of a sphere? Mr. Apple, I don't have that memorized. That's okay. You have it in your notes. 4 pi r squared. Yep. Very good. Again, you don't need that memorized. If you have it in your notes and you can find it relatively quickly, that's good enough. Okay? I do not need you to memorize any of these area, surface area, or volume formulas. They are always given to you. Even on the SAT, they give you these formulas. Okay, so we just need, well, we can simplify that a little bit, right? 1/2 times 4 is going to be 2, so it's 2 pi r squared. That's handy. What's r? What is the radius of our inside hemisphere here? Angel, do they give us the radius? No? But they give us something, right? What do they give us? The 1.86. Yeah, which is not the radius, but it is the what? Diameter. So we can find the radius. Agreed? Compare, if this is the diameter, then the radius must be what? How would we find it? Divide by 2, you've got it. So 1.86 divided by 2 is 0.9 0.93, he says. Can anyone confirm that? Yes, you agree. Okay, 0.93 centimeters is our radius of the inside hemisphere, so the smaller hemisphere. Okay, so we'll grab that number, use that down here. 2 pi times 0.93 squared. Which is, and let's leave this in terms of pi for now. How much? How many pi's? I want you to leave the pi. So in terms of pi, so multiply everything else. So 2 times 0.93 squared gives us something times pi. Let's go 3 decimal places. What do we get? What do you have? 3.46? Or is it, can we go one more? Or is that it? It's exactly 3.46?
Oh, not exact. I rounded it up.
4, 5, 9. Oh, that would be a 6, which would round it up. Okay, if I round to 3 decimal places, I get 460. Right. Yeah, so let's keep 3 decimal places. I'm going to try to be as exact as I possibly can. That pi is going to mean my final answer is either in terms of pi or an approximate decimal. Right? There's no getting around that. So let's try to keep the rest of it as accurate as possible. My general rule of thumb, okay, is first, check the directions of the question. They will often tell you, round your final answer to so many decimal places, or to the nearest hundredth, something. Okay? Whatever they tell you to use, that's what you need your final answer to be. Right? Let's say, for the sake of argument, they said to the hundredth on this one. That's 2 decimal places. Before you get to your final answer, go 1 more decimal place, at least. Right? This is not my final answer. This is only part of my answer. So I'm going to go an extra decimal place. So I'm going to go 3 decimal places with everything. That way, when I take my final answer and I add them all together, my errors down here, hopefully, will not add up to more than an error on that decimal, right? Does that make sense? Okay. And for the same reason, I'm going to leave it in terms of pi for now, until we get to the final answer. We can also think about this. Our other pieces, outside hemisphere, that's going to be like the same formula, isn't it? Also going to involve pi, right? That top ring, difference of circles, also going to involve pi, right? All 3 pieces, we expect to have pi in their answers. So if I add so many pi plus so many pi plus so many pi, I could factor out that pi and only involve it once. I mentioned this before. If you want the most precise answer possible, multiply by that decimal approximate version of pi 1 time. Save it for the very end. So that's what we're going to try to do. Okay, we got the inside piece. Let's find the outside piece. Same formula, which I already found out, like, oh wait, half of 4, I already got the shortcut version. Don't rewrite this again. You don't need to rework short versions that you already did. Start with 2 pi r squared. I now know any open face hemisphere, if I'm not, I'm not including the bottom circle on it, well, then it's just 2 pi r squared. Make it easy on yourself. So in this case, our r is, hang on, I'm going to use a different r. Let's use a capital R. That way we've got little r for the little circle and big R for the big circle, right? And then I'm not mixing things up. Makes it easier to follow along. All right, what's big R now? What's the radius of our outside circle? Anyone know? Andre? Not sure. Well, look at it this way. They've only given us 2 numbers, right? It's probably going to involve that 1.25, right? That's at least probably the number we need to work with, whether or not it's directly or not. We haven't worked that out yet. We said, hey, we used this number. That was the small one. I don't think the small one and the big one are directly related. There's like this gap thing here. They shouldn't be the same number, right? So let's look at this other number. And now looking at it from the diagram, can we work out, did they give us the radius or the diameter this time? What do you think? Is that the radius or the diameter of our hemisphere? It's going up and down now. This one is the radius, you're right. Because if we look at that, going from the middle out to the edge of our half circle here. So yeah, that's totally a radius. That is our big R. Okay, so bring that on down. 2 pi times 1.25 squared. So let's get to 3 decimal places in terms of pi. That outside surface area is let's see, do you have a number? Hmm, 3.145? Is that what you said? 315? One more time. 125. Thank you. Times pi, right? Right? Can we confirm that? And head's nodding. Okay, good. All right. We've got 2 out of 3. Last one. Now we just need the... ring around the top. Oh, I don't want to zoom in on that. So that area, we've already established. That's the difference of two circles, right? So we need the large circle minus the small circle. Yeah? Area of a circle is yes? Area of a circle? What's the formula? Pi r squared, very good. So I'm going to use big R for the big circle minus pi times little r for the little circle. Because those are the same radius, same radii as our hemispheres, aren't they? Yeah, they're right on top of each other, right? Same radii. So let's just use the same notation there. This is very common. Okay? Lots of geometry problems might involve two different sized circles. Okay? So great habit to capital R and lowercase r. Big R, little r. One for the big one, one for the small one. Now once you get into three different sized circles, then you got to come up with something else, subscripts or something. But this will do for us, right? And I can already see I can factor pi out of that. So that's pi times big R squared minus little r squared. And we already know our numbers for big R and little r. That was what, 9, 3? Yep. So now the ring becomes how many pi's? Yeah. What, 0.32? Really? You got 2.19. Those are vastly different numbers. Can I have a third opinion on that? This is 1 and a bit times itself is going to be 1 and a smaller bit. And this is less than 1 times itself is going to be more less than 1. So I'm expecting something more than 1 minus something less than 1 gives me something definitely less than 1.
So that is a pi.
Oh, you also included the times pi. Okay, I want in terms of pi for now. So what do we have? Point something. You said 3.1? 0.7 or 0.69? Round it 3 decimal places. You're saying 690? Oh, 6,976. So this. So to 3 decimal places would be 698. Right? I want to keep 3 decimal places for now. Okay, so there's my 3 pieces. And now add them all together. Total surface area is going to be 3.460 pi plus 3.125 pi plus 0.698 pi. And as predicted, we've got a pi in all of them, so we can factor that out. So just add those numbers together. And round to 2 decimal places, you get how many pi? Looks like at least 7 something, right?
7.23.
Okay, and so that's our final answer. Now let's multiply by pi. Round to 2 decimal places. What's our final decimal approximation? .880. Okay, so the 2 decimal places, just 88. And what were the units on this? Centimeters, right? So this is area, so this should be centimeters squared. Okay? Everyone happy with that? I am not happy with that. That is not what I had. Guys, we overshot. Something is wrong here. Can anybody spot what it is? The inside is bigger than the outside. Oops. Oh, well, you should have said something. No, absolutely say something. If the teacher is making a mistake on board, you call them out on it, okay? That is absolutely your job in this class. Call me out if I'm writing down something wrong. You're saying this should be 1.729? The 9 rounds up, so 30, okay. Okay, that sounds a lot better. And again, a little bit of pre-thinking here. This is less than 1, okay? And if I square it, it gets even smaller. That's what happens when you multiply small fractions times small fractions. They shrink, okay? So something less than 1, a smaller fraction, reduced fraction, times 2 makes it less than 2. So that should just be a mental check, like I should expect something less than 2 here. Let me put in my calculator, and out pops 3 point something, and I should be like, whoa, wait a minute, what happened? That is not the magnitude I was expecting. Right? Little mental check there. Very rough estimation, just so you know, what ballpark am I expecting? What are the limits? Should be more than this, or less than that. And at least do that, then you can catch those kinds of mistakes. Okay, so let's fix that. So that goes there. Which means we actually get how much? Start with how many pies? Now it's looking 3, 4, 5 some. 5.55? What's the third one? 3. 555. It's like a fake telephone number in the movies. Dial 555 1234. Okay, does that come out? Multiply that by pi, do you get 17 something?
17.4.
Perfect. There we go. That's what we were expecting. This is why we're practicing, right? Watch those mistakes. Very good. Any questions on this problem? Okay. I've hit all the major points I wanted to discuss with you. So if you would like to just start on the problem set now, we can do that. Or I have another example we could go through if you'd rather do that instead. So raise your hand if you just want to get started on the problem set. I just want to get my homework done as fast as possible. No? Raise your hand if you'd like to go through the other example. Few of you? Okay. So I'll go ahead and do the example. Those of you not interested, I am not requiring you to write this down. If you want to start the problem set, go for it. Okay? Those of you that want to see it, we'll keep going. How are we on time there? Which class is this? Is till 40. Okay. Got about 8 minutes. I'm going to speed through this, all right? This one involves stacking cubes on top of each other. Yeah. So we've got 30 unit cubes stacked in square layers to form a tower. Oh, I've done that with blocks before. Bottom layer measures 4 cubes by 4 cubes. Next layer, 3 cubes by 3 cubes. Oh, shoot, okay. I'm already going to start drawing a picture. And that's not a square. Square. There's my bottom layer, 4 cubes by 4 cubes. And then I need a 3 cube by 3 cube. And then next layer, 2 by 2, and then a single cube. Okay, so then we have a 2 by 2 and then 1. And those get stacked on top of each other. All right. And they want us to determine the total surface area of the tower of cubes. Interesting. So when I take, let's see, can I make this more clear? I'm going to change this to different colors here. Because what I need to do now is stack them on top of each other. All right? And so notice right away, just from this, I do not get all 16 red cubes. That surface is not exposed, right? These 9 cubes block some of that. And then these 4 cubes block some of that, right? And then this one blocks some of those. So I'm going to have a series of subtractions here. Yes? Sure. You kind of see that? Working through this. So I need to work out what all does get exposed. Okay? These are physical cubes. I've only drawn squares. So we got to think in 3D a bit. For every cube we've got, or at least every layer, we'll have the bottom side, the top side, and then around the edge, right? Stacking the cubes does not block the edges. Agreed? So we can always add up the perimeters. So we at least need perimeter 1 plus perimeter 2 plus perimeter 3 and perimeter 4. Yeah? And then the complete bottom of the bottom layer of the tower, that's exposed. So we'll have one instance of this square area, right? The bottom side of those cubes. Now we need the top of that layer. But we don't get the whole top, right? We only have the top minus the next layer covering it. Yeah? Again, I put this on top of here. Now I can visually, if I want to, spray this red, I'm going to have 16 minus 9, right? Is what we'll have out there. That's that face. Then we don't get to see the bottom of the blue layer at all, right? Because it's up against the red layer. How about the top of the blue layer? Well, the top of the blue layer is also covered by the green layer. So we've got the sides taken care of, but now I need to add the blue layer minus the green layer. And then I'm going to get the top of the green layer minus the purple layer. And then on the very top, I do get that purple layer does show up. I do get to count that one, right? That gets uncovered. Now, by thinking through this conceptually and keeping this as generic as possible and just coming up with something, is this actually the perimeter? No, it's the perimeter times the height of the cube. I don't care, okay? Just for reference. I want something to represent that. Because I'm just working out big picture, step one, find the surface area of a complex thing is add and subtract all the involved surfaces. Okay? So these all get added no matter what. And I'm also looking ahead. Hey, what else are they going to ask me? Suppose the number of cubes and the height of the tower were increased. So the bottom layer goes 8 by 8. Right? So we got 4 by 4, and then we add a 5 by 5 layer underneath, then a 6 by 6, 7 by 7, 8 by, right? More layers. And then 20 cubes. Oh my gosh. I could do it by hand for 4. I could keep counting up to 8. I really would like the general case, if I could find some shortcut formula to find 20 layers, that'd be great, wouldn't it? That'd save me so much time, because that's a lot of cubes to add. So that's why I'm trying to write this as general as possible. Because do you notice anything about the way I've written this? It's all addition, subtraction. Do those parentheses actually do anything to the computation? Do they actually change the order of operations at all? No. So ignoring those parentheses, does anything get reduced? I've got a negative A2 and a positive A2 right there. Isn't that going to be 0? Add area 2, subtract area 2, right? I've got a minus A3 plus A3, done. I've got a minus A4 plus A4, done. Huh. Those extra layers do not change the surface area at all. It's still just all those perimeter edges that are exposed, but the top and the bottom, let's still look down from above. It might be spread across a bunch of different cubes, but isn't my paint still only going to fill the 4 by 4 square? Hold on, guys, just conceptually, right? Do you see how that still works out to just that? Just the top and the bottom, plus all the sides. So all these extra layers do is add more sides. That's a much easier pattern to deal with. All right, that's it for that cool problem. You are dismissed. So long, farewell, enjoy the rest of your day.